Our next speaker is Ettore Aldrovandi from Florida State University, and I hope he appreciates I scheduled his talk in the morning so it would not conflict with the big football game versus Wake Forest this afternoon. Anyway, Ettore is a speaker, and his title is Determinant Functors for Triangulated Categories and Categorical Rings. Over to you.
Yeah, thanks, David, for the Rick, for the introduction and the football mention. But yeah, I am a soccer fan anyway, so that's one of the places where I didn't, take from Florida State. So anyway, this is I should mention this is a work in collaboration with Cindy Lester, who was at Florida State and now is at College of Worcester. And so I'm going to talk about determinant functors. Determinant functors is is a wide subject, and the interest for me is in triangulated categories in general, but in particular for triangulated categories that have also additional structures. In particular, they have a tensor product. Before we get into that, every time one mentions determinants, one of the questions is why are these things determinants in the first place? So let me just say a couple of words about the origin and the prototypical example, so to speak. So if you have your favorite vector space, finite dimensional vector space over field K, then a homomorphism can be represented, of course, by a square n by n matrix. And so if you take the top exterior power, the way that homomorphism acts is well known that it does by simply dilating the volume 4 precisely by the determinant of the matrix that represents that homomorphism. So once you have that, one thing you can do is simply take your category of finite dimensional vector spaces, and to every object, that is to every vector space, you can associate the top exterior power and record the dimension. And then, of course, to any, in fact, isomorphism between B and W, you can associate precisely the matrix that represents that homomorphism. So what you end up getting is a functor from the category of finite dimensional vector spaces, restricting your morphisms to just isomorphisms, to something that I can call lines, graded lines over K. So what that is simply the following thing. So the objects are just one-dimensional vector spaces over K, so copies of K, but not canonically so. And the second element of the pair is an integer, and the morphism is an isomorphism precisely when n is equal to n prime, and nothing otherwise. This is actually giving you a Picard groupoid, or in other languages, it's a symmetric categorical group. If you equipped the graded lines with essentially the tensor product, except that you keep track of the grading, and the symmetry is actually non-trivial because the symmetry is simply flipping the factors in the tensor product, but up to a sign. So there's a causal rule in force there, and this is essentially the prototypical example of what a determinant functor is. So this is the quote unquote, this is the categorification of the determinant. So the general definition originally due to the linear was the following. So it's an abstraction of what I just told you. So in the original reference, it's E is an exact category, which is a category in the sense Quillen exact. So category with short exact sequences. So, for example, you should think about an abelian category. P is a Picard groupoid. And so a determinant is a functor from the category of isomorphisms of E to P, equipped with additivity data that essentially say that whenever you give me a short exact sequence, then you have this morphism in the Picard groupoid. And then, of course, this is subject to a number of conditions that I will explain later in the context that it's the subject of this talk. So there are requirements of naturality, associativity, and commutativity, and we'll see that what they mean directly for triangulated categories. And so getting to that, so let me just quickly recall that a triangulated category is an additive category that has the following two extra, classes of data. So one is an equivalence, which is sometimes called the suspension. So it's another equivalence of T to itself. And then there is a class of so-called distinguished triangles that satisfy a set of well-known axioms, and we'll actually see some of those, in particular the octahedron, at work in a couple of slides. And the other thing is that the functor between triangulated categories, I call it exact. People call it exact if it preserves essentially the suspension and preserves distinguished triangles. Usually, the triangulated categories occur as essentially derived categories, or let's say homotopy categories of something much nicer. But it's known that this does not exhaust the possibilities. There are triangulated categories that do not have models. So in that case, one can translate, though, the idea of determinant simply copying the definition. So in particular, we have that it is, so the target will always be a Picard groupoid. Again, you have a functor from the isomorphism subcategory of T. And again, there are additivity data. This additivity data simply say that whenever you have a distinguished triangle, then you have to have this morphism into the in the Picard groupoid. And again, you have conditions of naturality, associativity, and commutativity, which mean the following. So, well, naturality is what you expect. So if you have a morphism of between two distinguished triangles, that ought to be translated in the appropriate way in the for the additivity data. And the commutativity arises because the direct sum is linked to the class of distinguished triangles by in this way, and therefore these two things are compatible in the sense that they are connected. The diagram is closed by the symmetry of the Picard groupoid, and the associativity is linked with the rest of the structure of the triangulated category. So here is the famous or infamous octahedron axiom. So basically, here you have two composable morphisms. So that's H here. For clarity, I prefer not to draw the octahedron as an actual octahedron, because otherwise you don't understand anything. So now these are given distinguished triangles that you can always build once you are given these morphisms. And the axiom says that you can always complete this diagram by filling in essentially the fourth distinguished triangle in a way that everything commutes. This is an extra corner that I usually add to remind myself of the remaining commutativity data. And in fact, this tells you that if you combine it with suspension, the autoequivalent, the equivalence of T, then this creates a sort of infinite periodic structure. So once you get there, what you have is that given this an octahedron like so, then the additivity data must be compatible with it, in the sense that if you start from the center of the octahedron, you start decomposing, you can do it in two ways. And then if you follow what's going on, you see that that will be closed by the associativity in morphism in the Picard groupoid. So it's a result by Browning in 06 that that if you define morphisms between determinants in the obvious way by natural isomorphisms, you obtain a groupoid, and the two functor that you end up defining over the category of Picard groupoids for a fixed triangulated category is representable, or maybe I should say co-representable, in the sense of two categories. So what that means is that there exists a certain nice Picard groupoid that's attached to your triangulated category that factors the determinant this way. And of course, the factorization is not exactly unique. Of course, you can't expect that, but simply says that if you do it in a different way, so with a G and a beta here, then there's a unique transformation from F to G that will make the two passing diagrams here the same. It's also true that, and proved later by others, that in fact this Picard groupoid, which is usually called the groupoid of virtual objects, has to do with the K theory of the underlying triangulated category. So the pi 0 and pi 1 of the groupoid of virtual objects are actually respectively the first and the zeros in the first K groups of T. Usually, so this is a universality statement. So this is usually called the universal determinant. It's remarkable that such a universal determinant exists, which was proved by Browning. So now this is all well known. The interesting thing is that poor as they might be in terms of the structure that they have, triangulated categories tend to have more structure, at least those that arise in notable examples, like the derived category of complexes of modules, for example. So they also come equipped with a tensor product. And so you have the idea of a tensor triangulated category, which is a triangulated category which also has a monoidal, usually taken to be symmetric monoidal structure, unidal, and compatible with the triangulated structure. I will tell you in a minute what that means in slightly more precise terms. So usually we refer to these functors as being biexact. People do not usually take for granted that a fixed list of axioms. So this is on the minimal side. It's known that there are possibly many more properties that one can decide to throw in as an axiomatization of what the tensor triangulated category should be. But this is a sort of bare minimum. What I like to point out is this very rough observation that once you have such a beast, that tends to behave in a certain way like a ring, or like a rig, because you don't have additive inverses in T, in the following sense. So suppose that you have you take direct sums in two ways. So I'm taking these two objects, and then I form one of the obvious distinguished triangles from the direct sum. On the other hand, I can take the an original distinguished triangle with x directs on y, and then tensor with z. So the exactness there means that this is compatible with the tensor product. Now, the usual axioms of triangulated category, they say that indeed you can't find a morphism here, which is in fact an isomorphism, and unfortunately is very highly non-canonical because cones in triangulated categories are notoriously problematic. But at any rate, it's a sort of way of finding a sort of distributor, in the sense that there is a morphism that says that the tensor product distributes over direct sum, and of course you can find similar structure maps in exploiting similar tricks. So this essentially sort of begs the question: well, does that the universal determinant for such a tensor triangulated category enjoy some property that is inherited from the tensor product? And I think a slightly better framework to think about this question is in terms of is multilinear structures. So the tensor product is in a sense is a bilinear thing. But there is nothing. But since you have to think about associativity and the pentagon, etc., because this is a monoidal structure, then it's probably best to think about n variables for an arbitrary n directly. So exactness. Well, what that means is that, first of all, that if I have, say, two variables, it means you have to be exact. That is, you have to preserve distinguished triangles in each variable. So you want to be a triangulated functor in each variable, as I defined at the beginning. And also there is this technical requirement that if you apply your functor to two suspended objects, then the suspensions come out in two possible ways, and then this will anti-commute. If you have n variables, you have to have basically these conditions for each pair of indices. So it's in fact known that if you take in general n exact functors, then you can assemble your triangulated categories in a gigantic groupoid enriched multi-category, in which precisely the multimorphisms from, this should have been a T. Those are simply the n exact functors that I defined before. So it turns out that you can do something similar for Picard groupoids. There is a parallel notion of being n monoidal in each variable with compatibility conditions for Picard groupoids. And so the question becomes simply an upgraded one, in the sense that if I start looking at the virtual objects, so what kind of structure do I get in the multi-category of Picard groupoids? So as a matter of notation, I'm kind of doubly underlying when I mean that I'm looking at a Picard at the multi-category that have been constructed out of an existing two category. So the first thing is one goes ahead and tries to invent an appropriate notion of what should be a kind of multilinear determinant. So in the first place, of course, what we want is an nth functor. And I'm going to require that this is a determinant in each of the variables. So what I mean is that if you keep all the other variables frozen except everything that's going on in the ith place, this is a determinant functor in the previous sense. There is, of course, a compatibility condition that you will have to write down if you have an isomorphism in one of the factors and a distinguished triangle in some other position. But the interesting thing is what happens in this case. So what I have is that, so the interesting condition that needs to be imposed is that if I have in two of the possible n factors, I have two distinguished triangles, then I want this diagram to commute. So I'm using the brackets to denote the determinant, and then I'm only writing the variables that are actually changing. So you see, if you split, so these are the additivity data. So what happens, for example, in this corner is that I'm breaking the first variable using the additivity data of this distinguished triangle, leaving the second variable alone. And then once you got there, you now you perform the same thing, but like breaking up the second variable, and then you do it also in the reverse order, of course. If you start in the other possible way, in the bottom line, and so what you find is that is the usual thing. So what you find is that these two here are going to be flipped, and of course, what you want is that the this diagram commutes by closing it with sort of canonical arrow that one can write down in every Picard groupoid, combining the associativity and the symmetric isomorphism. So these are requirements, and again, there is an obvious notion of that I'm not going to make explicit. There is an obvious notion of natural isomorphism between these upgraded determinants, so that you get the groupoid, which I call the groupoid of multi-determinants. So now there's a little bit of notation. So let me remind you that so if you have a multi-category, so if you have a monoidal category, a symmetric monoidal category, there is you can immediately construct a corresponding multi-category, but you can also go back and in fact these are adjoint two functors, where starting from a multi-category or a symmetric multi-category, if you care about permuting the variables, you end up with a sort of a monoidal category, sometimes called the free monoidal category over M. The objects are simply strings of objects in M, and composition is just a position. So where the morphisms then are induced by partitioning these sequences according to what the original multi-category says. So with that kind of notation, so this I want to remind you of that, because there is this funny symbol that I'm going to use. So the theorem is that you do get an equivalence of groupoids between the groupoid of determinant functors and the groupoid of n functors, within Picard groupoids, which are monoidal in each variable. So let's say exact, in the sense they are monoidal in each variable plus compatibility. There are compatibility conditions that that you have to take into account. They are very similar to this diagram, so I'm not going to write them explicitly. And so this object here, which is a string of virtual, so universal determinants for each one of these triangulated categories, is in fact, in a sense, is the object of this symmetric monoidal category that co-represents this functor here. So we find a complete analog of the single variable case. Moreover, there is functoriality also in this variable. So this is clearly functorial in this variable, but there is functoriality in a sense in this variable, according to the what the multi-category of triangulated category says in how you should compose the morphisms. There is a condition, though, that you can take the whole thing, but you have to restrict to multi-morphisms, that is n exact functors that I say are Verdier, meaning that they have to preserve a certain structure. So let me briefly explain what that means. So there is some diagram that's called the 9 diagram, according to Beilinson, Bernstein, and Deligne. So you can form diagrams which are grids of distinguished triangles. All of them are distinguished triangles. It commutes, and the condition is that, as before, that you have to have a non-anti-commute in this corner. So you can consider this morphism, this diagonal morphism here, and then you can complete it to a distinguished triangle. And so we say that this 9 diagram has a Verdier structure if essentially this arises from a combination of 3 octahedra. This is a kind of a technical. I'm not expecting to, that people will be able to follow, but this is just to point out that there could be extra structures that are embedded in these kind of diagrams. So the way it works is that essentially the morphisms that are constructed here, in particular, the existence of this object is the combination, as you can see, of certain cones that you see here. And they all involve the object A. And so eventually you'll be able to construct from this 3rd octahedron the morphism that sits here. So this is a theorem by these people that say that if you have a square like this, can always be completed to a grid, a 9 diagram, by exploiting these constructions. And other people have actually shown that if a tensor triangulated category comes from nicer structures, then diagrams tend to have these kind of hidden Verdier structure. So we are saying that a multi-exact functor emits a Verdier structure if whenever you feed 2 distinguished triangles, you get a grid like that. And we say that F is Verdier if the diagram that you get here emits a Verdier structure in the previous sense. So the previous theorem says that basically you have to restrict to this kind of functors in order to account for this functoriality here. So now what about categorical rings? So that's the other side of the story, in the sense what happens on the Picard side. So everyone has their favorite, favorite definition of what a categorical ring should be. So I give you 2. So one of them is biased in the sense that I can call a Picard groupoid a categorical ring if there is a second monoidal structure, which is bi-exact. So in particular, it will distribute over plus unital and associative. So this is biased because then you have to explicitly think about the associativity, pentagons, etc., for this extra monoidal structure. On the other hand, there is an unbiased version where you can say that a categorical ring is a monoid in pick as a multi-category. So it's or if you prefer thinking about operads, then it's going to be you're going to be thinking about an algebra over a certain kind of operand. So there is also a parallel version for in the sense of thinking in an unbiased fashion for the triangulated category. So to get to the point, so the theorem is the following: that if you give me a tensor triangulated category in which the tensor product is Verdier, in the sense that I explained before, then the universal Picard groupoid is a categorical ring. So I certainly don't think about giving you a proof, but the idea is simply the following: that if you take your tensor product, you follow with the universal determinant, so you have some sort of multi-determinant there, and universality says that you can essentially split it, and then that's essentially what you're after. But of course, the devil is in the details. So this, in order for this to work, there are technical conditions that need to be imposed. As a corollary, of course, what we get is in the case, if you can make a correspondence with K theory, then K0 is the ring as it should be, and K1 is going to be a K0 T bimodule. So as an outlook, so categorical rings, I mean, Picard groupoids have a Poznikov invariant, categorical rings being Picard groupoids, if you forget the second monoidal structure, also have a Poznikov invariant, which in this case is a class in topological Hodgkin homology or MacLane homology, depending on your taste. So question that has inspired this work is, what does this class, if anything, say about the original tensor triangulated category? In particular, there are certain elements in K1 that can be sort of explicitly detected. Does this class allow us to do that? And I think that's it. So thank you.